Welcome to lesson 101. This is well, in my mind, this will be the first lesson most will want to watch. If you have no knowledge or extremely little knowledge about electricity, this is where you want to start. The first question we must ask ourselves is, what is electricity? Most of us have a pretty good idea. So let's get started. What is electricity? Let's consider a copper atom. The nucleus has protons, which are positively charged. They're in red. And neutrons, which are neutral in charge. I color-coded them green. This is my cartoon view of a copper atom. All the black dots are electrons orbiting the nucleus. They are black because they are considered to be negatively charged. For an item to be a conductor, there are essentially three things that are needed. Number one, some free electrons in the material. Number two, that outermost electron must be very far out from its nucleus and alone in its orbit. So if the outer orbit contains only one electron and it's quite a ways out, meaning there are multiple orbits under it, that electron can migrate from atom to atom relatively easily. And as I said, there will be free electrons in the material as well. So if there is current in the wire, what we really mean is there is organized electron flow. Here I've invented the world's most impossible wire. It is a copper wire made of copper atoms, one atom wide and one atom thick. An impossible thing to build, but let's just pretend that I build it. So the positive terminal of my battery is connected at one end, the negative terminal at the other. The positive terminal will create an electric field that will pull electrons in. They will migrate along the wire to the positive terminal, pass through the battery, and come out the negative terminal. This electron flow is what we call electricity. So there are a few rules that go with all this. The first one is very simple and it's almost obvious. If the switch is closed on the left, that means it's on, so current flows. If you open it, like we did on the right, that means the switch is off and the current just doesn't have anywhere to go, so it stops flowing. So rule number one is electrons can only flow in a complete or closed circuit. Now, the next rules, I'm going to bring them up all at once, is that we've got to come up with a way to describe the current flow, the electromotive force pushing the flow, and any resistance trying to stop the flow. For that, we use Ohm's law. The voltage is the electromotive force pushing the current. The resistance in ohms is trying to stop the current from flowing. The current itself is the result of the struggle between these two. So voltage, electromotive force, we measure in volts. Resistance, we measure in ohms. And the current, we measure in amperes or amps. The reason they represent current as an I is that means intensity. So the higher the current, the more intensity, or the more intense the current is. Ohm's law can be organized in this pie chart, which makes algebra really easy. And you can see the relationship. If I have electromotive force divided by a resistance, I know how much current I have. So if I have 10 volts divided by 5 ohms of resistance, I'll have 2 amps of current. Or if I have 2 amps of current flowing across 100 ohms, I must have 200 volts applied. So you can, if you know any two, you can calculate the third. Now, what's also important is to understand that power is measured in watts. That takes the form or the abbreviation P for power. So voltage in volts times amps equals power in watts. You can do a lot with just these four formulas. If you're studying for your ham radio exam, I would suggest you learn all four of these. Not just to pass the test, but because you really want to understand this. It's not hard to understand, and it's very fundamental to radio, and really to electronics in general. So far, we've been talking about DC current like out of a battery. DC current will not get us to the world of radio. You'll notice that the arrow, the gray arrow, is time moving forward into the future. If you walked that arrow and you looked at the blue line is voltage from a battery. You'll notice the voltage never changes. And the polarity never changes either. Now that's fine for powering a flashlight or your car's starter or something like that. But we can't make radio waves with DC current. We've got to move to the world of AC for that. You'll notice that the voltage changes from positive to negative very regularly. That means the current reverses direction very regularly. What you're looking at, that graph, that's the graph of a sine wave. The most common thing you will encounter in radio is the good old sine wave. Now, the reason they call it a sine wave will become a little more apparent as you study, but the sine function from trigonometry can be used in such a way that if you know where in the cycle you are and you know your voltage, the sine function tells you what the voltage will be at any other point in the cycle you want to consider. That becomes really important later on. You won't have to do the math, but in the radio world or the RF world, that becomes extremely important. And just as a little note, the symbol for an AC generator, which we call an alternator, is the little circle with the sine wave symbol sitting on its side. I don't know why it sits on its side, but it does. Now, let's look at the sine wave. You might be thinking, well, that's funny. You've got positive current, but when your negative current happens, that would be negative power, so they're not equal. Well, they are, because we really don't care about positive and negative. All we're saying is the current flows in one direction for half the cycle, and then the other direction for the other half. In fact, if I flipped the bottom up and just forget polarity, we don't care about it, you'll note that there's as much power or energy in the bottom half of the cycle as the top. So it really doesn't matter. The polarity really is almost meaningless. So let's go through the sine wave and see what really happens. We'll step through it slowly. We're going to start at time 0. At time 0, there's no voltage, there's no current, there's nothing. There's just nothing's going on. As soon as we leave time 0, we are approaching the voltage level at time 1. So immediately, one end of the wire becomes positive, the other end becomes negative. Current starts flowing. The electrons start jumping from atom to atom. Once we get to 1, the voltage is at a maximum. So eventually, we're going to get to 2. When we get to 2, there's no voltage again. Current has dead stopped. As we approach 3, voltage and current are going the opposite direction now. Notice before the positive was on the right, now it's on the left. As we approach 3, the voltage will peak and the current will peak with it. Once we start heading toward 4, the voltage starts to drop, the current starts to drop. When we get to 4, we're really right back where we started. So that's one cycle of a sine wave. The voltage, therefore the current, in the electrical outlets in your house go through that cycle 60 times per second. Now 60 seems fast, but it's actually tremendously slow. If you're listening to your favorite radio station at 98.1 FM, the carrier signal, that is the sine wave signal being fed to the tower and the antenna, are going through this cycle 98,100,000 times per second. If you're listening to your local AM radio station that is at 1,000 on the dial, well, that 1,000 is 1,000 kilocycles, so that radio signal is going through this 1 million times per second. And that brings me to this point. We say 1 cycle per second is 1 hertz. This is an abbreviation because saying cycle per second got a little tiring. So now we say hertz. We abbreviate that to Hz. If we had 1,000 hertz, that's 1,000 cycles per second. That'd be 1 kilohertz. That AM radio station at 1,000 on the dial, or 10 on the dial, is actually at 1 megahertz. It's at 1 million hertz, or 1,000 kilohertz. Now 1,000 megahertz is 1,000 million hertz, and that's 1 gigahertz. These three abbreviations, kilohertz, megahertz, and gigahertz, especially kilohertz and megahertz, you'll use a lot and you'll see them a lot. But now you see something important, and that is the number of cycles, and that is the number of current reversals in a second, can be extremely high in the radio or RF world. I use the term under the second bullet point, RF. Get used to hearing me say that. In the radio world, we describe RF as any voltage or current or any wave front in the RF spectrum. In other words, it is oscillating from about maybe 30 kilohertz up to 300 gigahertz. So get used to RF. Get used to me saying RF and get used to talking about RF. You have now entered the RF world. You've entered the radio world, but we call radio RF. Radio, frequency, energy. So I've made a big deal about the sine wave. And the sine wave is the fundamental building block of radio. But once in a while, you might encounter a complex wave. A complex wave might be something like this. This is a capture of my voice coming out of a microphone on the microphone cable. It is not a sine wave, as you can tell. It is very far from it. The human voice has a lot of harmonics and subharmonics mixed together. So get used to seeing things like this, but this is not a radio wave, and it won't pass through an RF circuit very well unless it is superimposed on a radio wave. That is an RF frequency signal. Let's move on to understanding radio. We've kind of laid the groundwork of what electric current is and how electric current is electricity. Now let's take a look at a couple of things that I did not learn early on in my study of radio, starting at the age of 12. It took some time before I understood what I'm about to present. You can get by without knowing this that follows, but believe me, when you start to try to understand the operation of antennas and coax feed lines and tune circuits and things like that, what I'm about to present becomes very important. Don't worry about why it's important. Just try to grasp the next few minutes of my presentation. Okay, within the world of electricity, I see it as two fields in one. The electrical world is where we're using electricity as a conduit of power to power up a saw or a fan or a light. Then there's the world of electronics. This has to do with using electricity as a conduit of information, whether it is to store information like in a computer or to transmit information as in radio, where you're transmitting radio waves for the sole purpose of sending information, even if all that information is your own human voice. For the purpose of wiring a house or understanding how things are powered electrically, we can get away with thinking of electron flow as electricity. But radio is a little different. There's an interesting relationship between electron flow and electricity that becomes very important if we're going to understand radio. See, in the RF world, that is radio frequency world, electron flow and electricity are not quite the same thing in that electron flow isn't quite the same thing as radio wave propagation. Even the radio wave going down a coaxial cable, which is actually electric in nature, it's not the flow of the electrons that we're paying attention to. I'll explain what I mean in a moment. This is extremely important later on when you try to understand how antennas work or antenna feed lines like coax cables work. It's not that important when you consider a circuit that is handling information or storing electricity in a battery or something like that. Now we're really going to get down to it. If electron flow is the movement of electrons in a conductor, we've got to keep in mind that electrons move rather slowly. You've heard that electricity moves at the speed of light. Well, it does. But electrons don't. Now you can research the internet and ask the internet, how fast do electrons move in a circuit or a wire? Or how fast do electrons move in electricity? The answers will vary from a few centimeters per second up to a third of the speed of light. I've been in radio a long time. I have a degree. I have several licenses and certificates. I can't tell you how fast electrons move. In my engineering books, particularly those on antennas, the discussion of how fast electrons move is never mentioned. Only the movement of charges. So perhaps charges is what we should be looking at. The propagation of the force of the electron flow does travel at near light speed. The electrons aren't moving all that fast. And the best way to explain this, and I found this some time ago, I wish someone would have taught me this 50 years ago. Let's say I'm holding a garden hose in my hand, or at least I'm holding one end of it. You're going to hold the other end. We're both going to hold the end, or each end, of the garden hose 4 feet off the floor. The hose is 30 feet long. I'm going to reach into my pocket and I'm going to fill this garden hose with marbles. The marbles exactly fit the inside of the hose. When I get the hose so full of marbles that they fill right up to the top of my end of the hose, because you're holding the hose at the same height off the floor, your end of the hose will be full of marbles as well. So if I push one more marble into my end of the hose, a marble will pop up out of your end of the hose and fall on the floor. So let's do that. I'm going to push the marble in at 1 marble diameter per second. So I'm slowly going to push this marble in. As soon as I get it all the way in, the marble at your end has jumped out of the hose and fallen on the floor. But I'm moving the marble at 1 marble diameter per second. There's hundreds of marbles between me and you. But you don't have any problem grasping the concept that each marble pushed the next marble. And that's why, even though the marbles are moving very slowly, the propagation of marble movement actually moved very fast, didn't it? It's the same thing here. When we speak of those electrons jumping from atom to atom, in advanced physics, that's called charge movement, or the movement of a charge. The electrons might move from atom to atom slowly, but the wave front, the beginning of the movement of atoms, moves very quickly. The same as with the marble. If you lock this into your head for a few more lessons, it'll come back later, and you'll be glad you learned this. Because you will often hear that electrons don't move very fast. No matter how fast someone tells you they move, they will tell you that they don't move nearly as fast as the speed of light. Now, I can't prove to you, myself, how fast electrons move in a wire, but I can prove to you how fast electricity or RF currents move in a wire, and I will do that in a later lesson. I will prove to you that it is very close to the speed of light. In some instances, we can show it at close to 95% of the speed of light. Through the air, as a radio wave, it's the speed of light. But in conductors, it does slow down a little bit, but it's nowhere near as slow as the movement of individual electrons. So if you have to, listen to this a couple of times until you get it. Although I really think the marble analogy works great. As soon as I heard that, it locked into my brain and I was fine. Well, thanks for listening. I hope this has been helpful and interesting. The next lesson will be DCL 102. In that lesson, I'll talk about electric current and magnetism and how they're partners. And anywhere you find one, you tend to find the other.